So, now that we're done with Unit 2, we can begin Unit 3. Unit 3 is where we really start getting chemistry different than other science courses, because Unit 3 we're now going to start dealing with atoms, what we're actually made of, and beginning to see how they might interact with each other. So first of all, we're going to talk about what does an atom look like, how do we know it looks like that, and the way that this has changed throughout the years. You'll recall that one of the hallmarks of good science is that science changes over time. As our methods improve, what we know about the world can get more and more refined with more and more evidence. We're going to begin the discussion over 2,000 years ago, around 400 BC even, with this guy Democritus. Democritus was a Greek. He was one of the ancient Greeks. This was probably in the time after the Peloponnesian War, I believe. Is that the right one? Whatever the war with the Persians was. Athens really helped to become the victors in that war and were able to put a lot of money into architecture and science. So Democritus was an ancient Greek, and he came up with this idea that there was a certain smallest bit of matter that you could not divide anymore, and he called that atom, from the Greek word meaning indivisible. He actually did not have any science to back this up. This was the answer to a logic puzzle, something called Zeno's paradox. Basically, the idea, and I can illustrate this better in class next time, that the Greeks mathematically could not prove that if a turtle, a tortoise, very slow, and the Greek hero Achilles were in a race, that if the tortoise had a head start, they couldn't show mathematically where Achilles would ever beat him, because Achilles would catch up to where the tortoise was, but then the tortoise would have gone a little bit farther forward, and Achilles would catch up there, but by that time the tortoise would have gone a little bit further forward, and catch up, but a little bit further, catch up a little bit further, and they couldn't mathematically show a point where Achilles would be able to beat him. So Democritus said, well, eventually you'll get to a point where it's so small you cannot break that up anymore, and that's an atom. Again, there weren't any experiments here. The Greeks weren't very big on experimentation. That's why a lot of their science is a little bit fuzzy. But a much more famous Greek named Aristotle had a different idea about matter, that everything was made up of these things he called elements: earth, fire, wind, and water. Sometimes this spirit was added into this, and because Aristotle was so much more well known and his ideas were more accepted, Democritus's ideas fell by the wayside. So then we have to fast forward much, much further into, in fact, the 1800s, to this guy here, John Dalton, an English school teacher actually. And he had been taking a look at what had been changing in science in the last decade or so. In the 1790s, some new ideas were coming out. First of all, the idea of the law of conservation of mass. Remember, a law is an observation that's always true. That when a chemical reaction occurred, the mass before the reaction and the mass after the reaction were the same. Mass wasn't gained or lost. Two, something called the law of definite proportions, that when a compound formed, let's say water, water always had the same amount of oxygen and the same amount of hydrogen in it, whether it was water from a lake or water from a river or water from different parts of the world. So he put these ideas together into a new idea of the atom. I'm not sure if he was aware of Democritus's ideas, but they were quite similar in some ways. Dalton's atomic theory, the explanation to fit these observations, remember is what theory means, is that matter is made of atoms, these small little things that you can't break up anymore. Atoms of a certain element are identical, so any atom of carbon is like any other atom of carbon. All atoms of gold are exactly identical to each other, but carbon and gold are not like each other. Atoms cannot be divided, created, or destroyed. Atoms are always going to combine in whole number ratios, so that would explain water, you would have one oxygen and two hydrogens, not half a water and one hydrogen, for example. And in a chemical reaction, atoms are rearranged. Maybe they go from one place to someplace else, but you're not making them according to Dalton. They're just rearranging. Pretty good. It explained these two laws he had. So his model, if you wanted to draw it, models are never 100% accurate, and scientific models get better and better. His model looked like just a round ball, solid little round ball. And that's Dalton's model. And it's good. It explains a lot of things. And in fact, his model came out in around 1808. We have to fast forward almost 100 years to the late 1800s before we get another major advancement. So, scientists loved playing around with electricity in the late 1800s, and one of the devices they had was called a cathode ray tube. Cathode rays, in fact, until just recently were in all computer monitors and TVs. Basically, what they were seeing was when electricity was passed through this cathode ray, you can see a ray tube down here, a glowing line would shoot across the ray tube to the other end. Now, this line, they didn't exactly know what it was, but they did know that it could be bent by magnets or charged objects. For example, they saw that if you bring a negatively charged object towards the glowing line would bend away from it. Instead of going straight across, it would bend. And from what they knew about electricity, they knew that whatever made up this glowing line had to also have a negative charge, because like charges repel. So, using those observations, in 1897, a guy named Thomson, J.J. Thomson, Joseph John Thomson, came up with this model, this explanation, an improvement on atomic theory to fit this. He said that, well, an atom then, although it is neutrally charged, has to have a negative part and a positive part. And in fact, they did find the positive charges later. So this changed the model. It was no longer a solid ball that you couldn't break up anymore. You could split off positive and negative parts. His model, it's described in most books as a plum pudding model. But that's an English dessert. We don't really have it in America. And I'm not sure anyone really eats plum pudding anymore. I like to think of it as a chocolate chip cookie. You've got the big cookie part itself. It's a big spread out positive charge, so the positive charge is sort of diffused through the whole area with little negative charges stuck to it. The value of all that spread out positive charge and the little negative charges is going to be equal. So that's Thomson's model. And it works. It works pretty well because knowing that there's electrons really helps make some advances. But there's more change still coming. Fast forward, that was in 1897, so about 13, 14 more years up to 1911. 1911. There's a test of the Thomson model being conducted by Rutherford usually gets the credit, but he didn't actually do the experiment himself. He had his assistants Geiger and Marsden do this experiment. But what they did, they were using positively charged alpha particles. These are radioactive particles. They're not very dangerous radiation. In large number they can be, but one of the good things about radiation, it's easy to see where it's going. All you need is a piece of camera film. And what they did, they had something that was making alpha particles, and they shot them towards a piece of gold foil. And what they were trying to do was calculate if Thomson's model was correct, then there should be a certain amount that, since the atom itself has a slight positive charge in Thomson's model, then these positively charged alpha particles should be just slightly pushed to the side, just slightly. And they would be able to measure this angle of deflection and figure out exactly how correct his model is. Well, they saw something that they didn't expect. Most particles went straight through the gold foil as if it wasn't even there. No deflection. Some of these particles were deflected a small amount as they expected. Some of the particles were deflected a lot. Some of them almost straight back at the where they started from, which meant then that something was going on here, something different. Think about that for just a minute. What this had to mean was in the new model, there couldn't just be a spread out positive charge like Thomson thought. That positive charge had to be concentrated, very, very concentrated positive charge, and that positive charge had to be in the center. So what this new model now, what we call the Rutherford model, said was that the atom is mostly empty space. The positive charge in the atom was very small and was in the middle of that empty space. For comparison's sake, imagine a marble in a football field, a football stadium even. That's how small the nucleus is compared to the rest of the atom. So that actually explained a whole lot. It helped make better predictions, but now there was a problem. Where was the negative charge? If the nucleus is so small and the atom itself is so big, where was the negative charge? And you can pretty much guess then that it would have to be around the nucleus, filling up some of that empty space, but where exactly? And that's what we're going to focus on for a lot of the rest of this unit. Where is the negative charge? What is an electron? What do electrons do? Because that's going to provide the answer for a lot of being able to guess what happens when two chemical compounds react with each other. We are going to stop there for today.